From now on, I will talk about cosmological perturbation in the several series of the video. This content is based on the Bauman cosmology textbook and the lecture note. So in this video, I will talk about cosmological perturbation with the Newtonian gravity. This is the already we discussed this in the previous video. So the such a cosmological perturbation mean that we will keep the inhomogeneity. For the standard cosmology, the homogeneity is assumed with FLRW metric, but the realistic universe has some structures like the galaxy cluster and some cosmic web and network. Such a small partial inhomogeneity is evolved over the cosmic history. And such a cosmological perturbation provides the formalism and the frameworks to explain such an inhomogeneous universe. So we will expand the small perturbations around the background of the FLRW metric with the assumptions of the homogeneities and isotropy. Depending on the physical scale and the regime, we can consider two different theories. First of all, the simple version is for the sub-horizon scale and the non-relativistic regime, we can apply the Newtonian gravity. But if we consider the super-horizon and the relativistic effect, relativistic effects mean that we will consider some radiation. The velocity is best and the general relativity is necessary. So in this video today I will focus on the Newtonian gravities for the cosmological perturbation, and in the next video I will talk about the general relativity. So first of all, the Newtonian perturbation, the first case is the assume that there's a no gravity and a no expanding universe. Then there's some material of the cosmological component can be expressed as a fluid dynamics. This dynamics is governed by the conservation equation. There are two conservation equations. The first one is the continuity equation, and the second one is the Euler equation. Each equations correspond to the mass and the momentum conservation respectively. So this is the continuity equation with the energy density, energy flow, and this is Euler equation. If we multiply the mass, then this is correspond to the momentum density and momentum flux. On the right hand side, this is the term of the pressure. So the gradient of the pressure, this term, that keeps the force, the external force. And we can perturb the some linear order for the energy density, momentum, and the velocity around the background with homogeneity and the static one. Then we can extract the first order term, just the linear equations for the conservations, the following here. And we can introduce the two quantity. The first one, the density contrast, defines as delta rho over the background energy density, and the sums of the speed shear scale, which is the ratio between the momentum perturbations and the energy perturbation. Then the for this linear conserved equation, taking the time derivative for the first one and the gradient for the second one, then these two terms cancel each out. And the delta p can be written through with the delta rho with the sound speed. Then we can obtain the equation for the delta rho or density contrast delta. So the density perturbation satisfies the following equation. Here there are no gravity and expansion, so the linear perturbations just propagate as a sound wave. So it has a plane wave solution with the following dispersion relation. Now we can ask the gravity. Now there will be the gravitational potential, capital Pi. This gravitational potential is satisfied by the Newtonian Poisson equation. This is similar to the electric field. Now the conservation equation has the additional term for the Euler equation. Okay, sorry. So again, Newtonian. So the Poisson equation. So the gravitational potential will contribute the Euler equation. This will give the gravitational force. And similarly, we can perturb the gravitational potential with the linear order. Then the changes term is for the Euler equation there will be the linear term, and for the Poisson equation also there is a linear term. Then similarly we can obtain the equation of the motion for the perturbation by time derivatives and gradient. The new terms is the gravity contribution. Then the dispersion relations are following in the previous place. This gradient scales becomes the momentum. So the frequency has a two term, which comes from the pressure, because the speed of sound comes from the delta p, the momentum perturbation, and the second term is the gravity contribution. Then we can bind that depending on the sign of the omega scale, the solutions are quite different. We can define the Jeans wave number kji. So if the wave number k is larger than the kj, the Jeans wave number, then the frequency is positive. So it propagates through with some specific oscillation frequency. This means that the gravity contribution is smaller than the pressures. But if the wave number is smaller than the Jeans wave number, then the frequency becomes negative, so it has exponentially growth solution. And in this case, the gravity contribution is dominant compared to the pressures contribution. Also, such a small k mode mean that the wavelength correspond to this k mode is larger than the Jeans wavelength. So such a gravitational instability on the large scale is called the Jeans instability. And this provides the Newtonian mechanism for the growth of the cosmic structure. And also we need to add the effects of the expansion. And we know that there are two different quantities, tx plus the distance. The first one is the physical distance, and the other one is the moving distance. And these are related with the scale factors a. And we can define the physical velocity. Now here, those are just the time derivatives of the both sides. Then for the a dot, we can define the Hubble parameters as a dot over the a, and the x dot, a times the x dot can be defined the v. So the u's correspond to the physical velocity, and the v's correspond to the moving velocity. And depending on the derivatives with regarding to the r or the x, there is three factors that are different. For the partial derivatives, the delta r is the same with the 1 over the a times delta x. And for the time derivatives, this is quite complicated. For the delta t with the fixed r has a relation with the delta t with the fixed x and additional term is because some specific function up depending on the x, also it is depending on the r. Then by the chain rule, there is additional term will appear. The first term is just the fixing x, and we can fix the r, but by the chain rule, the partial t, partial x, and the big string R. So this term will appear. So now the conservation equations in the expanding epochs so also changes. For example, for the continuity equation, from the physical coordinate R, we can obtain the cumulative coordinate x. Now this partial derivative has one of the I factors here, and for the time derivative also there is additional term here. And for the velocity, we can decompose like that by using the delta x times the vector x equal to the 3 because the three-dimensional space. Then we can obtain the continuity equations with the following form. So the expanding epochs give the additional term with the Hubble parameters and one of the I factors. Similarly, we can obtain for the Euler equation. There will be the additional term in here and one of the I factors for the delta x. Similarly, we can obtain the linearzed conservation equation. The zero source gives the background continuity equation, and for the first order equations the following. There will be the Hubble parameters and one of the I factors in front of the delta x. These two comes from the expansion epoch. And similarly, we can Fourier transforms. Then we can obtain the equation of the motion for the density perturbation with the expanding epoch. Now we established the Newtonian gravity to describe the cosmological perturbation and the inhomogeneous universe. So now we'll apply this formalism for the matter perturbation in the realistic situation. Because the matter is non-relativistic, the velocity is slower than its mass, unlike the radiation. But the problem is that before the recombinations of the early universe, the baryon matters are tightly coupled to the photon. So it behaves like the baryon photon fluid. So the baryon has the relatively large sound speeds and finite values of the C's. If we calculate the James wave number, it has also the finite value. So C's is large. This means that the James wave number becomes small. And the gravitational growth starts when the moving wave number is smaller than the James wave number, but the kj is small for the baryon before the recombination. So the most mode does not satisfy these conditions, so the baryon perturbations does not grow. So that it tightly linked to the photon. But rather than the baryon, we can also consider the cold dark matter. But before that, let's talk about the what happened for the baryons. But after the recombination, the baryon and the photons are decoupled, and the sound of the speeds are drop. So the C's go to 0. It's because the photon has the equation of the state with the p equal to the 1 over the 3 low, but for the matters, p equal to the just 0. So similarly, the delta p also has a 0. So the 0 sounds of the speed. So the James wave numbers are proportional to the 1 over the C's. So the 0 sounds of speeds mean that the James wave numbers become very large. So the condition for the density perturbation growth can be easily satisfied, and the baryon perturbations start to grow. But in contrast, the cold dark matters does not have the sound of speed for the OR approach because the cold dark matter does not link to the photon. So that this can satisfy the growth conditions always for the most of the K mode. So the dark matter density perturbation can start the growth much earlier than this can provide the seed for the gravitational potentials and the density perturbation. So this dark matter's density perturbation start the earlier growth, and this makes the important role for the cosmological perturbation. So now let's talk about how can we deal with this dark matter perturbation with the each approach, because in the universe there is a radiation dominant approach, and after that the radiation and matter equality, there is a matter dominant one. Then again, let's talk about the linear equation for the density perturbation. The final results are following, but we will consider that the cold dark matter, and cold dark matter has a zero sum of speed, so that we can ignore the effects of the pressure. So the equations that simply written by the following form, and the last introduce the solution of the delta k, the density perturbation in the k mode has the following form, whereas these decompositions mean that the first terms correspond to the growing mode and the second terms for the decay mode. And the delta k only depends on the k mode, and the d, this is just a function of the time t. So let's talk about the matter dominations first. For the matter domination, the scale factors evolve to the h to the t a go to the t to the 3 over 2, and the background density laws are proportional to h to the minus 3. So the Hubble is 2 over 3t, so we can replace it here, and for the anode density is h to the minus 3. So the equations can be written only with the function of the time. Then if we try the power solution, then we can obtain the two solution for this second order differential equation, and the growing mode is correspond to the t to the 3 over 2, and this can be written in terms of the scale factors a. So the point is during the matter domination, the matter perturbations that grow as proportional to the I. Delta k is proportional to the I. Now let's turn to the radiation domination. Universe starts the radiation dominations, and you will go to the MD era after that, but the radiation RD era is quite difficult compared to the MD. Now here's the scale factors evolutions changes also for the Hubble, and for the anode density one, the radiation contribution can be ignored due to the acoustic oscillation. So the delta R can be neglected. So the remaining term is just the contributions from the cold dark matter anode density. But this cold dark matter anode density is the smaller than the radiation anode density during the RD, so that we can ignore the all the binary term compared to the first two terms. So the just remaining term is this second derivatives around the first derivatives, and by using the Hubble's as a function of the time, then the result is just given by the cold dark matter perturbations values R and I. So during the radiation domination RD approach, the CDM, the cold dark matter perturbation, grows logarithmically. This effect is called the Master-Jarrow effect. So today we talk about the Newtonian gravities for the cosmological perturbation. This Newtonian gravities is applied to the non-relativistic and subhorizon region. We first talk about the conservation equation, the continuities around the early equation, and we asked the epochs of the gravity by considering the Poisson equation and also the adding the cosmic expansion. And we applied this Newtonian gravity for the cold dark matter because the for the baryon one, baryons the coupled to the proton before the recombination, so that this cannot go. But the cold dark matter has the zero sound of the space, so that we can easily satisfy the Jensen instability condition to close the perturbation. For the cold dark matters, it has a different behaviors of the density perturbation growth. During the RD, the perturbations go with the logarithm proportionality, so the growth is very slow. This is a Massager effect. But after the matter's radiation equality, universe is in the MD, and then the density perturbations goes to the proportional to the scale factors A. So today we discussed the very simple versions of the inhomogeneous universe with the Newtonian gravity version, but we will extend to express the superposition and the relativistic mode. This requires the generalization to the relativity.